Are you having trouble finding a spanning tree in your connected graph? Is your local string theorist trying to convince you that his 10-dimensional manifold is just 3 dimensions? Oh! Well, have I got the perfect solution for you? Introducing set theory and the axiom of choice. Using the power of numbers, order, and functions, this bad boy can solve so many problems. For just $10.99, we will send a trained professional to your house and solve all your selection problems. Call 555 Set Theory to grab this opportunity today. That's 555 Set Theory. The axiom of choice cannot be proven to be true. Proffesional Math LLC will not be responsible for any paradoxes or shattering of reality caused by the axiom of choice. Any risk pertained by using the axiom of choice, however, is reduced by 100% if you hit the like button and hit subscribe. To learn more, continue watching for an informative video about the axiom of choice.
The axiom of choice is a statement about sets. As such, we should probably talk about them. So, as kind of a consequence, we kind of want to build up all of mathematics using the concept of set so we can use the axiom of choice everywhere. So what is a set? Well, a set is a collection of mathematical objects. And we say that sets contain elements. If a set A contains, for example, X, we write X is in A, where that E symbol means in. And if every element of A is in B, we call A a subset of B, and we write A and that subset symbol right there. So A is a subset of B. Finally, let's get to our notion of equality for sets. And this is that two sets are equal if and only if they have the same elements. So, we'll also assume the axiom of unrestricted comprehension.
What is an axiom?
An axiom is an assumption we make. So for the axiom of unrestricted comprehension, we are assuming, given a sentence as X, we can construct a set of all objects X satisfying the sentence.
And from this, we can define the pair of two sets, the union and intersection of a collection of sets, and the power set of a set. The pair of A, B is the set A, B can be defined as X equals to A, or X equals to B. The union of the collection of sets C is defined as X that exists at big X belongs to C such that X belongs to big X. The intersection of a collection of sets C is defined as X for all big X belongs to C, X belongs to big X. The power set of a set X, P of X, is defined as X is a subset of big X.
I've got you now. Under these rules, the set R, which equals the set of X such that X is not in itself, can be defined, which causes a paradox. Here's how. Consider the set R itself. Does R belong in R? If it does, then R does not belong in R by definition. Thus, it is impossible. Consider R again, but instead ask, does R not contain R? If R does not contain R, then since R is a set of all X such that X is not in X, R should be in R by definition. But then R is in R, so we have a contradiction. So the set R implies a contradiction either way.
Oh no! We can't build mathematics with a contradictory system! No!
So we don't do that unrestricted comprehension. Instead, we work to axiomatize set theory, so that we have stricter rules on what we can or cannot do. For example, we axiomatize the notion of equality as the axiom of extension. A set A is equal to a set B if and only if their elements are the same. So let's do some more.
First, we gotta assume something very important. We have to assume that there actually is a set. And so let's do that. There's a set, and let's call it Q. Cool. Now, we can move on to defining some axioms. Our first is the axiom of specification, which says, given a set A and the sentence S of X, the set of all elements x of A such that S of x is satisfied exists and is represented by this weird thing. And it's a subset of A. You sometimes see it called the axiom of subsets. And this is what patches out Russell's paradox. Okay, here's how. So let A be a set, and define B as the set of all elements of A, set of all elements x of A, such that x is not in X. So can B be an element of A? If so, then either B is in B, or B is not in B. But this is what leads to Russell's paradox in the first place. It's a very similar thing. The only thing that changes is that X has to be in A. But here's the kicker. We can get out of this because we have this clause that says, okay, if this is only what happens when B is in A. So, B is not in A. Thus, there's no set that contains all sets, which is kind of sad, but we got rid of Russell's paradox. Hooray! And also, from this axiom, we can get a set with no elements, called the empty set. And it's written as this funky symbol, kind of 0 with a slash through it. And we define it as the set of all x in Q such that x is not equal to x. Since no x will ever satisfy that, it's empty, there's no elements. And a set is allowed to have no elements. So, this is a pretty useful set, and we will use it later. Interestingly enough, intersection can actually be defined from specification. And here's how. Let C be a non-empty collection of sets. Let A be a member of C. This way the intersection of all sets in C can be defined as the set of all x in A, such that for all big X in C, X is in big X. Wonderful. You can see this has the nice properties of intersection. X being in A just makes it within A. And any element in the intersection has to also be in A, because A is in the collection. Wonderful, right? Wonderful. So, let's talk about some more axioms.
The axiom of pairing. Given any pair of sets A, B, the set A, B exists. We can get the set only containing A by using pairing on two copies of A, and since a set is defined by its elements, A, A is just A. The axiom of union. The union of a collection C of sets exists. If the collection C is a pair of sets A, B, we can simply write down the union of the two as follows. Union of A, B equals to A union B. A similar convention goes for intersections. For any set big X, the power set of big X, P of big X, exists.
Well, I don't think that you can define a function only using the language of set theory.
Actually, we can. However, we need to define the notion of an ordered pair. An ordered pair AB is an object, such that AB is equal to CD, if and only if A equals C and B equals D. And we can define it using purely sets, but it's a bit complicated. So here it is. The ordered pair AB can be defined as a set, whatever that is, which is basically the set containing A and the set containing A and B. So let's verify it has the properties we want. A, B equals A, which is A, B equals this, whatever the set definition is, equals CD, whatever the set definition of CD is, if and only if A equals C and B equals D. And let's verify that.
If the tuple AB has only a single element, then the set of A equals the set of A and B, since B is in the set of A and B, which equals the set of A, B equals A. Conversely, if A equals B, then the set of A equals the set of A and B by extension, and the tuple of A and B equals the set of A. Suppose the tuple A and B equals the tuple X and Y. If A equals B, then the tuple A and B and the tuple X and Y each only have one element, so X equals Y. And since the set of X is in the tuple AB and the set of A is in the tuple XY, we have A equals B equals X equals Y. If A is not equal to B, then the tuple A and B and the tuple X and Y each contain only one set with one element, the set of A and the set of X, respectively, and thus the set of A equals the set of X, which means A equals X as desired. The other elements in both the tuple A and B and the tuple X and Y must be equal to each other, and thus the set of A and B equals the set of X and Y. As such, B is in the set of X and Y, so either B equals X or B equals Y. If B equals X, then B equals A as well, which contradicts our assumption. Thus, B equals Y and QED.
We want to have a set of all pairs such that the first position is an element of big A and the second position is an element of big B. The Cartesian product big A cross big B is our answer and is the set defined as A, B such that A belongs to big A and B belongs to big B. This is the naive definition, but we can construct it using our axioms. Fun problem, eh?
A relation R from a set big X to a set big Y is a subset of big X times big Y, where if x, y is in R, we write x, r, y. Functions are relations from a set big X to a set big Y, with the property that for all x in big X, there is a y in big Y, such that x, y is in F, and for all x in X, if x, y is in F and x, z is in F, y equals z, where y and z are in big Y. So if x, y is in F, we write f of x equals to y. So we have families, and families are just functions, but more focused on the outputs than the function itself. We call the outputs of a function its range. So consider a function x from a set I, called the index set, to a set x. The range matters more than the function itself. And the range is called the index set, and the function is now called a family. And the value of a function x at index I is called a term of a family and is denoted x sub I. So the Cartesian product of a family, I promise this is relevant. A family, let's call it a big X sub I, is the set of all families x sub I with x sub I in big X sub I for each I and I. So, yeah. I wonder what else we can do with sets. Oh, what about numbers?
Turns out that we can build numbers from our axioms. Let 0 be the empty set phi, 1 be the set phi union the set containing phi, and the successor, the number plus 1, of any number x be x union the set containing x. This process goes on forever, but what if we wanted to build up a set that contained all of them? The axiom of infinity allows us to do just that. The axiom of infinity states that there exists a set containing 0 and the successor of each of its elements. Let's call the set allowed by this axiom suck. Other sets that could satisfy the axiom of infinity's guarantees are called successor sets. And we define omega to be the intersection of all successor sets that are subsets of suck. Basically just all of the natural numbers. We can prove the P&O axioms from them, and also all of arithmetic. But we won't get into them. We can even define an order on them by the subset relation. A is less than or equal to B if A is a subset of B, and it has all the properties of a total order.
What the celery is a total order?
Well, I'm glad you asked.
So we can think about ordering a set in many ways. First, let's talk about partial ordering, which is a relation less than or equal in a set X, where if X, Y, and Z are elements in the partial order of big X, all of the following are satisfied. So, X is less than or equal to X. Basically, X is less than or equal to itself, which is pretty obvious, since X is equal to X. And number 2, if X is less than or equal to Y, and Y is less than or equal to X, X is just Y. Makes sense. And number 3, if X is less than or equal to Y, and Y is less than or equal to Z, X is less than or equal to Z. So, less than or equal is transitive. And we can see that the numbers are partially ordered by the subset relation. And every number is ordered. And if every element is ordered, i.e. for any two elements x, y in a set which is partially ordered, either x, y, as x is less than or equal to y, or y is less than or equal to x. It can only be one or the other. Not one or the other, but either one or the other. It could be both, especially in the case of equality. But that's what a total order is. Okay, let's just get rid of some terminology. So we call x a maximal element in a total order of big X. If the order is such that every element in A in big X satisfies that A is less than or equal to X. And similar for a minimal element, so we call X a minimal element in the total order of big X if the order is such that every element A in X satisfies X being less than or equal to A. So, this is the extent of the useful things we can talk about with our current tools about order. And so to do more interesting things about order, we have to talk about the axiom of choice. Woo, we promised we'd get to that. One of us did.
The axiom of choice. The Cartesian product of a non-empty family of non-empty sets is non-empty. This is not really helpful in why we call it the axiom of choice, so alternatively we could define it as follows. For every non-empty collection C of non-empty sets, there exists a function f from C to the union of C such that for all x in C, f of x is an x. The reason why we call it the axiom of choice is that f chooses one element from each set in the collection C. This is a powerful tool. It gives us a lot of, dare I say it, choices. This axiom leads to prominent results that we shall leave a proof for in a future video. Zorn's lemma and the well-ordering theorem.
So you might be wondering what Zorn's lemma is. So Zorn's lemma says that if big X is a partially ordered set such that every chain in big X has an upper bound, then X contains a maximal element. That's the lemma. And it's called a lemma because it follows from the axiom of choice. So let me explain this a bit better. So chain is just a totally ordered set. And we call a chain in X when a subset of X, when considered partially ordered in its own right, turns out to be totally ordered. And this is true by the axiom of choice. So, what's the well-ordering theorem? That's the other thing we promised we could prove from the axiom of choice. Well, we should first talk about what a well-ordering is. A partially ordered set is called well-ordered if every non-empty set of it has a minimal element. Any well-ordered set is also partially ordered. Consider for every xy in a well-ordered set the subset only containing these sets. By assumption, either x is less than or equal to y, or y is less than or equal to x, because one of them has to be a minimal element. So it's kind of guaranteed that the whole set is totally ordered. That's cool. So now we can talk about the well-ordering theorem, which states that every set can be well-ordered.
Wait, what? Every set? Even the real numbers?
Yeah. And you know what's even cooler than that? What's even cooler is that these turn out to be equivalent the axiom of choice as well. This means that we can prove the axiom of choice from these. Is a theorem of both of these things. Zorn's lemma leads to the axiom of choice, and so does the well-ordering theorem. And you know what else we can do with this? We can prove that every vector space has a basis with this. That every connected graph has a minimum spanning tree. All from choice! Choice gives us the power!
Yeah. Wrap it up, please.
So, what we've seen here can be used to build up most of mathematics. We've omitted two axioms from set theory that are usually there for the sake of brevity, but in the future we'll make more in-depth set theory videos. And the axiom of choice is a really powerful tool. It's used a lot in central analysis proofs, especially in limits over functions. So what does set theory and the axiom of choice say about determinism and free will? Yeah, you tell me.
Ask a philosopher or a constructivist. I'm not getting into it right now. Sorry.
What about Banach Tarski?
Ask a philosopher about that, for goodness sake. Okay. So now that you've watched the vid, I hope you know that all you need is set theory and the axiom of choice.